So now, we have a mathematical interpretation of our cost function. That's what we have now, right? So let's now put all of this together into a math formula so we can close the circuit. In the equation, y equals mx plus b, m and b are the parameters. They're the coefficients. That's what we want to find, the optimal values for. So during the training process, there will be a small change in those values. So let that small change be denoted by d, as in delta. The value of parameters will be updated as m equals m minus dm and b equals b minus db, right? Or m equals m minus the change in m and b equals b minus the change in b, right? Respectively. And the goal here is to find those values of m and b in y equals mx plus b that give us the lowest possible error. Okay? In other words, the values which minimize our cost function. So rewriting the cost function gives you what you see on the screen. Again, the idea is that by being able to compute the derivatives, okay, or computing the slope of the function, then we can find the minimum of the function, the cost function. So let's start with the parameters. Okay? We start with the parameters that we need to solve, and that is m and b. M is equal to m plus the change in m. Same thing with b. B is equal to b plus the change in b. So, given the cost function for n number of samples, you have a summation of errors, which is the cost function that you see on your screen. Let's just call the cost function j, and the cost function, it's a function of both weights, in this use case, m and b. Last, I want to substitute y primed minus y with error, because that's really what it is. It's just a measure of the error. I've said that a few times now. The learning rate. I haven't really talked about the learning rate that much. The learning rate, it's the size of the steps taken to reach that minimum, or the bottom. Okay, that's the learning rate. We can cover more area with larger steps or a higher learning rate, but if we do that, then we run the risk of overshooting the minimum. Okay? On the other hand, if I make my learning rate very, very small, then it will consume a lot of time to reach the lowest point. And by time, it's not just time, it'll be computational power as well, right? Because I'll be burning the CPUs, GPUs, etc., right? Running through this algorithm repeatedly. So I need to find that Goldilocks value, right? Usually people will set the learning rate somewhere between 0.1 and 0.25, right? But that differs. So here is a visualization that gives an idea about the learning rate concept, and see how, we want to reach that minimum point with the minimum number of steps, right? And that is the optimum learning rate for a problem. Okay, let me make a point. You can manually set the learning rate. We saw that when the learning rate is too low, it takes a lot of steps to converge. On the other hand, if the learning rate is too high, gradient descent is going to fail to reach the minimum because it's going to bounce back and forth over the minimum. It'll never get there. So we need to find the sweet spot for that. Okay, derivatives. Derivatives. You don't need to crack out the old calculus book and learn derivatives. Everything that I'm covering here is to give you an intuition behind machine learning and deep learning. But derivatives are germane to everything that we cover in machine learning and deep learning, okay? Because it is the derivatives that give us really what we need, what we're looking for in optimization problems. Optimization algorithms, like gradient descent, they use derivatives to actually decide whether to increase the weights, M or B, in order to increase or decrease any objective function. Think about what a derivative is. A derivative in calculus, it's basically comparing two variables in an equation. Like I said before, if I change this variable, how does that impact the other variable? In machine learning, at least, the learning part, right, is all about taking the cost function and see what happens if you change the coefficients, right? It's a very clear use case for a derivative, right? If I change the coefficients, what does that do to the error? Does it increase it? Does it decrease it? If we're able to compute the derivative of our cost function, we know in which direction we need to take our coefficients, M or B, in order to minimize the cost function. You don't really need to take years of calculus and advanced calculus to understand that concept, right? At least you know what you need for machine learning as a developer. I'm not saying it's not important, you don't need it, but as a developer, as a programmer, somebody who's actually going to put nose to grindstone and implement this, it's really unnecessary. Really what you need is to understand the concepts behind a few things from calculus. I'm talking about if you want to be a programmer again, right, in the data science space, right? Leave the high-level math to the math nerds. Frankly, there are libraries, right, that do the math for you. You just need to understand what it's doing, which is the purpose of this episode. In addition to understanding conceptually what a derivative is, we primarily will be dealing with three concepts from calculus: power rule, the chain rule, and partial DiffEqs, or partial differential equations. Let's start with the power rule. The power rule in calculus, it calculates the derivative of a variable raised to a power. Remember, we chose mean squared error as our cost function, and in part, I'll be honest, mean squared error, it was a selfish choice because a function raised to a power, it simply uses the power rule in calculus to get its derivative. And the power rule in calculus is dead simple. For example, if we have a function similar in shape to our cost function, which is f of x equals x raised to the, let's say, nth power, then the derivative of that is the value of the power times any constant times x raised to the n minus 1 power. Simple, right? Dead simple. You don't even really need to use your brain, right? You only need to use your eyes and poof, right? You just did calculus. So 3x to the 5th power, let's say that that's the function, then the derivative of 3x to the 5th power is 15x to the 4th power. That is the power rule. And really, I'm not sure how much more value I can add to that. Okay, so we just discussed the power rule, right? In calculus, there's also the chain rule, right? And the chain rule is used in gradient descent. The chain rule is used for calculating the derivative of composite functions. The chain rule, it can also be expressed in Leibniz notation, as you can see here. If a variable z depends on the variable y, and that variable y depends on the variable x, okay? So that y and z are dependent variables, then z, via the intermediate variable of y, depends on x also. This is called the chain rule, and it is mathematically written as you see on your screen here. Okay, that's the chain rule in calculus. Here's one of the intuitions that I use to help me understand the chain rule. If I have, let's say, a value that's in miles per second, and I need that in miles per hour, then I can use the chain rule and convert miles per second to miles per minute, and then miles per hour, right? That is the chain rule. In machine learning, we're going to use the chain rule in a similar way. Instead of miles per hour, it's going to be the cost function per weight, right? Which relates to M and B. I'm assuming that we have multiple coefficients. Okay, using the power and the chain rule for derivatives, we can now calculate how the cost function changes relative to M and B. This deals with the concept of partial derivatives, which says that if there is a function of two variables, then to find the partial derivative of that function with respect to one of those variables, you simply treat the other variable as a constant. So, consider our cost function. We said that it has the general shape of y equals x squared, and we know that x equals z squared. Then by using the chain rule, the derivative of y with respect to z can be calculated as dy over dx times dx over dz. We know that dy over dx, if we take these individually, equals 2x. And dx over dz equals 2z. Remember, they were both squared, right? So dy over dx is equal to 2x. Dx over dz is equal to 2z. So now, remember, this is about taking individual points of view and collapsing their perspectives. If we combine them together, or we chain them together, then dy over dx equals 2x times 2z. That is the chain rule. So let me provide you with some clarity. Instead of x and z, think of m and b, right? And our cost function. In our use case, those are the two attributes that we're solving for, and we're using the cost function that I'm going to call j, right, for that. So in our case, it's going to be dj, or the change in the cost function, with respect to db, or the change in the coefficient b. It's going to be equal to 2m times 2b. Okay, and this will be clear with an example. The last thing that you need to know is some more about the partial derivatives. So let's say, for instance, that we have a function, and that function has two dependencies. I'm going to show you f of x equals x to the fourth power plus y squared. The partial derivative of the function with respect to x will be d of f over d of x, and that'll equal 4x cubed plus 0, because we're treating the y, in this case, as a constant. The partial derivative of the function with respect to y will be df over dy equals 0 plus 7y to the 6th power, because we're treating x as a constant. This just takes knowledge of the power rule of calculus and the knowledge of the derivative of an integer, it's always 0, and we can compute the partial derivatives. That was a general calculus overview with only what we need out of calculus as it applies to machine learning. Let's now look at how that applies to our problem. Our cost function, which I'm going to call j. It has both an m coefficient that is dependent upon and a b coefficient. So it is j of m comma b. Let's explore that a little more, because we now have enough background to cover how to calculate gradient descent. Let us now apply the knowledge of these rules of calculus in our original equation and find the derivative of the cost function with respect to both m and b. And I'm going to start by revising the cost function equation. J of m comma b equals 1 over n times the summation of the error from I to n squared. This is what we need to get the derivative from, and we need to keep getting that derivative so we can use this as a beacon to tell us how to change the coefficients of m and b. Do not be intimidated by this. This is actually very simple. Remember our friend, the chain rule. That is all that we did with the cost function. For simplicity, let's get rid of the summation sign. The summation part, it is important, especially with the concept of stochastic gradient descent, or SGD, versus batch gradient descent. During the batch gradient descent, we look at the error of all of the training examples at once, while in stochastic gradient descent, we look at each error at a time. However, just to keep things simple, we're going to assume that we're looking at each error one at a time. Now I want to calculate the gradient of the error with respect to both m and b. Let's start with m. Take the derivative of the error with respect to the weight m. Let's substitute the error with y prime minus y. Okay, let's do one last substitution. We know that y prime is actually the algorithm. Y prime, our prediction, that equals mx plus b. So let's substitute the algorithm in for y prime. This means that x, b, and y are all constants. Okay? That means that the derivative of the error with respect to m is equal to x. Finally, you can do the same for the derivative of the error function with respect to b, and when you do that, you'll see that the result is 1. Plugging the values back into the cost function and multiplying that with the learning rate, that gives us our complete equation. Remember the chain rule, right? The change in the cost function over the change in m equals 2 times the error times the partial derivative of the error with respect to m. The partial derivative of the error with respect to m, we said, is x. Now let's just add our learning rate and we're good. Here is where we tie everything together. 2 times the error times x. It only determines the direction that we need to go. We're doing this derivative here, we're going through this so we can calculate the direction. Okay? The derivative gives us direction, the learning rate tells us how big of a step we need to take. Again, context, right? Remember, the cost function graphs as a parabola. You're somewhere on this parabola. You keep getting the tangent on the line at a particular point in the line, right? That's what the derivative is doing with respect to one of those coefficients. And that's simply telling us, do we need to go this way or do we need to go that way? How far we jump, that is the learning rate. That tells us how far we need to go in that direction. Let's do the same thing with the change in the cost function over the change in b. Okay? 2 times the error times the learning rate. Remember, the partial derivative of the error with respect to b is 1. So we now have equations that allow us to calculate which direction to change m and b, and by how much. If you made it this far, congratulations. You know more than most people, frankly, in this field. If you're not with me up to this point, please watch this again. I promise you this is right and you can get it. Let's start with m. We have an existing value of m, and we need a new value of m. So the equation is m equals m sub 0 minus the change in m. The change in m, it comes from the derivative of the cost function with respect to m. We already solved for that, so we now know that the derivative is the error times x times the learning rate. By substitution, then the new value of m equals m sub 0, the original m, minus, by substitution, the error times x times the learning rate. Do the same thing for b. The new value of b equals b sub 0, or the existing value of b, minus the error times the learning rate. That's it. Now, this 2 in the equation, it really isn't that important. It's not really significant, since it's just saying that we have a learning rate that's 2 times as big or half as big. So frankly, you can just get rid of the 2. It doesn't really matter in this case. So ultimately, this entire episode boils down to 2 simple equations which represent the equations for gradient descent, the optimization algorithm. Again, all of gradient descent boils down to these 2 equations. For m and b, okay, and the next position parameters, the original m and b, and the new values for m and b, okay? So to solve for the gradient, we're going to iterate through our data points using the new values of m and b, and we're going to compute the partial derivatives once we get to the optimization function, giving us new values for m and b. This new gradient is going to tell us the slope of our cost function at our current position and the direction we should move to update our m and b parameters. The size of our update is controlled by the learning rate. The entire point of this episode was to demonstrate the concept of gradient descent and where it fits into the overall machine learning training life cycle. Remember, gradient descent is where the learning comes in machine learning and deep learning. We use gradient descent as our optimization strategy for linear regression by drawing the line of best fit to measure the relationship between square footage and condo prices, study time versus grades, heights versus weights, or whatever, right? Doesn't matter. Whatever has a linear relationship. It's important for you to note that the linear regression example, I only chose that for simplicity, but this applies to many other machine learning techniques as well. Logistic regression, deep learning, perceptrons, over and over and over, we're going to use gradient descent. It's fundamental that you understand this optimization algorithm. So let me summarize here. We started off, as you can see in the diagram, with data, right? Data that we've processed, and that data we said is more or less in a tabular format. We took one row of that data and we fed it to our algorithm, which is y equals mx plus b. We calculated a prediction, okay, from our algorithm based on the input values that came from our data. So now we have y prime as our prediction, and we went to our data set and we put y over here, which is our goal, which is what we expected. We went over to our cost function or our loss function, and we said we're going to take y prime minus y. We're going to see how far off our prediction was to what our goal was. After we did that, we went up to the optimization algorithm, which is gradient descent. And in gradient descent, we learned 2 things. We learned which direction we needed to change our value of m, up or down. That was the purpose of the partial derivatives. And we applied a learning rate that showed us how far we wanted to change the values of m. For instance, if I said, hey, we need to go in this direction, okay? We need to go in this direction, that's from gradient descent. Learning rate says we need to go this much, okay? Now we have new values for m and b. We send that over to our algorithm and we adjust m and b in our algorithm. Then we take a new row of data with the new m and b values there. We make a prediction with the new m and b values, and we go around and around and around in that loop until we find the best possible values for m and b. Okay? And that learning again occurs in the optimization algorithm. Let me tie this off by telling you what happens after. At this point, what we have done is we have discovered the best values for the coefficients. You no longer have an algorithm that you are training. You now have a model, right? That model has been optimized, right? The values for those coefficients have been optimized. So y equals mx plus b, with the actual values of m and the actual value of b, that is your model. Simply an equation is what your model is. I can now take that equation and package it up. That's my machine learning model. And now I can send new data to that model and it will simply output predictions. We're done with the training phase. We now have an equation that's optimized, it's trained on the data set that we have. I simply give that input values, it computes and spits out a prediction. Again, my name is Ernesto Lee. Thank you very much for your time.